So this is the lecture number 2. So the previous lecture, so we have been discussing about the soil salinity, how we're going to represent soil salinity, and then what is the impact of soil salinity on crop production. Okay, and also the and soil salinity measurements, so soil and osmotic potential, and all those things we discussed in lecture number 1. And the lecture number 2 will be focusing on the soil, the salt balance, and then Sodicity, and then the leachate fraction. So all those things we're going to discuss in lecture number 2. Okay. So since the salinity, soil salinity influence the crop production, so we need to understand how to estimate the relative, crop production or reduction in, yield. So that's called this relative yield reduction. So we discuss the reduction in relative yield. So that is, let's say, YR, which is equal to EC0 minus ECE divided by EC0 minus EC, we can put T, or we can, let's say, threshold, that's called a threshold EC into 100. So where YR is this relative yield, so we put like a YA by YP, so that is YA is the actual crop yield divided by YP is the potential crop yield or the maximum crop yield we expect. Okay, EC0, that means without when the crop production is happened when the soil salinity is within the limits, so you get the maximum yield. So Y and then ECE, so which is saturated soil extract, EC of saturated soil extract, and EC0 by ECT into 100. So this is only possible. If you look at the graph between relative yield and then the EC here, this is ECE. So extracted soil, the soil extract, saturated soil extract. So then you get like, so initially, even the salinity increases, up to certain salinity level, there is no yield reduction. So let's say YR is equal to 1. If the YR is equal to 1, so that means the actual yield will be equal to potential yield theoretically. And so that can happen till some soil salinity levels. Okay, so we call this is ETC. So EC, let's say this is a threshold, right? And then after that, if you continue increasing the soil salinity, the yield is going to decline linearly down. And some point you get 0 yield, and we call that is EC0. So EC0 is the electrical conductivity for which the yield is going to be 0, or the relative yield is going to be 0. So that means the actual yield is going to be 0, and then you get YR is equal to 0. Okay, so this equation clearly represents the effect of soil salinity on the yield. Okay, so here 3 terms you can observe. One is ECE, that is the soil salinity of the, the actual soil salinity or present soil salinity or current soil salinity, whatever it may be. So that's the thing. And so when you increase that, so up to some certain point, that is, the yield is not going to decline. Okay, because just like we required salts, the plant also required salts. Okay, that's fine. And but what happens if you have more salts? You get increase the BP, blood pressure, and all those things. So similarly, the crop is not going. Certain salt levels is fine. After that, it doesn't good for crop growth. So that is ECT. So then, if you still it's increasing, then the plant yield reduction will be taking place. So till EC0. Okay, so this is the graph. So if you see, this is only possible when EC. So what happened? So when ECE, sorry, when ECE is less than ECT, less than ECT, so your yield YR is going to be 1, less than or equal to, less than or equal to ECT, then YR is equal to 1. Okay, so that's clearly seen from this equation. If you substitute it ECE, for ECE for, sorry, ECT for ECE on the numerator, you get 1. Okay, and this equation only valid if the ECE greater than ECT. So then YR is going to be 0. So if it is greater than, then YR is going to be 0. Okay, so this with this there is an example. Let's do the example. So let's say EC of wheat field. So EC of a wheat field. Okay, EC of a wheat field is equal to 7 decisiemens per meter, and ECT. So that is for which you get the potential yield, right? So ECT will be 4 decisiemens per meter. So ECT is the threshold for which you get the maximum yield. Then after that, your yield is going to decline. Okay. So the yield, the actual yield, let's say, the yield at so the yield at ECE greater than 22 decisiemens per meter, so that will be 0. So that means this will be equal to, so that means what? EC 0 will be equal to 22 ds per meter. So that means the last one. So yield is going to be 0. Relative yield is going to be 0. Okay. So then you have to find out what is, the question is, what is reduction in the yield? Reduction in the yield. That's the question. So if you understand, the crop is the wheat crop, and the soil has electrical conductivity of 7 decisiemens per meter, and the threshold electrical conductivity for which you expect maximum, I mean, there is no yield reduction, let's say. There is no yield reduction, that is 4 deci per meter. So that's the threshold. And then so there is a zero yield, right? Zero beat yield can happen for a soil electrical conductivity or salinity of 22 deci per meter. So that will be EC 0. Okay. So then what is the reduction in the yield in that case? So that means this is a threshold, right? And this one is the, I mean, the yield 0 can happen with this soil salinity. This is the maximum soil salinity. Okay, with that yield will be 0. And then current, I mean, the soil electrical conductivity or the soil salinity is 7 deci per meter. So if the soil salinity is 7 deci per meter and the wheat crop, so what is the yield reduction you can expect, right? So why there is yield reduction? Because if you look at this, so for 4 deci per meter, there is no yield reduction. So since the soil has 7 deci per meter, so definitely there is yield reduction, but you have to find out how much is the yield reduction. Okay, that's the question here. So we're going to use the above equation to find out, yield reduction. That's YR. So the YR equation, you see, YR is equal to EC 0 minus ECE divided by EC0 minus ECT. So that's the threshold into 100. So EC0 is 22 deci per meter because for EC of 22 deci per meter, the yield will be 0. So minus equivalent. So that is 7. Okay, that's the soil EC. And divided by, again, 22 minus, what is the threshold? It's a 4. If you multiply it by 100, you get 83.33%. Okay, and therefore yield reduction. So this is yield reduction, sorry, this is the relative yield. You have to find out the yield reduction. Okay, so in order to find out yield reduction, so let's see what is the YR. YR is equal to actual yield divided by potential yield of yield, right? So that will be, what you got is 83.33%. Okay, and then you get actual yield. Let's say this is YR dash. Okay, so Y actual dash will be 83.33 multiplied by YP. Okay, similarly, you get a relative yield of, like, there is no yield, I mean, actual, so there is no yield reduction. In that case, YR will be 100%, right? There is no relative yield will be 100%, which will be equal to YA divided by YP, let's say. So in case of YA will be 100 multiplied by YP. Okay, there are two cases. This is one. Now yield reduction, the percentage of yield reduction will be so that will be actual yield. This is a change in the actual yield, right? Change in the actual yield divided by actual yield. This is what? This is a yield reduction. Okay, so YA will be 100 into YP. I'm just going to take YP out. This is 83.33 into YP, and divided by YA is 100 into YP. And now you get, this will be 16, you can write 16.67 divided by 100. Okay, or we can say 16.67%. So this is the yield reduction because of the salinity. Okay, this one. So now let's talk about the salt balance. Right. So the salt balance. So let's assume this is the field, the form field. Okay, so this is the form field, and let's talk about what are the inputs and outputs. So salt balance means we are talking about the mass balance. So we also call conservation of mass. So the inputs here are definitely, one is irrigation. Let's denote with I. The other one is rainfall, R, and there could be groundwater input. Okay, so we are talking about the waters, because that's the driving force for the salts. So what are the ins and what are the outs? So the salts which are present in irrigation water, salts present in rainwater, salts present in groundwater, so that can be influencing the total salts present in the soil root zone. So what we are talking about, this is our interest is soil root zone. So let's assume that this is the soil root zone, right? This is a soil root zone. Yeah. And what else could be the, these are the water inputs. So sometimes you also add this agricultural inputs like fertilizer and all that also contains salts, right? So this is called ag inputs, right? And then now let's talk about, outputs. A different color for outputs. For outputs, so this will be, uh, let's say, plant uptake, water plant uptake. So that is a P. And this will be surface drainage, let's say SD. So it's kind of runoff, right? And so this is DD, that's a deep drainage. Okay, so these are all the outputs we can expect, right? And then since you're talking about the mass, okay, so they could be, the parent material. So that also, so once it's intact with water, so that's the parent material is going to, a salt presence in the soil can dissolve in, soil moisture. So that's, let's put as, because that's also going to add, so that's called MP, that's a parent material, MP. Okay. And then, so since this is adding, right? This is adding to the soil mass. This is adding to the soil mass. So then the, okay. Yeah, so this is, so let's say this is from salts present in, let's put the S. And this is agricultural inputs, because that's MA, which you're applying it down, right? Down to the, and then since P is going up, so there's a possibility of MPs because the precipitation. precipitation is also possible, because when the concentration is more, so it's going to, there is no space for dissolution, so it's going to obviously, some salts are going to precipitate. Okay, so let's put things in the balanced equation we call conservation of mass. So according to the conservation of mass, so what is that? Input minus output is equal to the change. Yes, so that's the thing. So inputs here, what are the inputs? So the water inputs are the, let's say, the irrigation, that's the volume of irrigation water, and then the corresponding concentration of the salts. That's the one thing. Plus, what are then the rainwater, volume of rainwater added to the soil, and then the concentration of salts. Plus the volume of groundwater added to the root zone, and the corresponding concentration of salts. Okay, so this is all water, and then we also see some salts adding to the system. So those are like mass of salts from the parent material to the soil system. So that is Ms, plus is the mass of salts added through fertilizers, that is Ma. So these are all inputs. These are all inputs. Now, what are the outputs? So we are going to subtract the outputs. So one is volume of deep drainage and the corresponding concentration, salts concentration, plus the volume of surface drainage and the corresponding salts concentration, and then plus the plant water uptake. So that is volume of plant water uptake, PW, let's say, and the corresponding concentration, this PW, right? And then the plus, so there are some masses, that is precipitation. MP is the salts, they precipitate, okay, and that's it. So this is all the outputs. So the inputs and then outputs, which will be like a change in the salts, we call delta M SW. So change in the salts in the soil water. Okay, so that's the balance. Now for the steady state equation, definitely we are going to cancel some of the terms, assuming that whatever the salts which are present before the season will be the same as the after the crop season. Okay, so that means there is no change in the soil salinity levels before and after. So before, suppose you have soil salinity of the field, let's say 4 deci per meter, and at the end of the season, what you harvested the crop, at this end of the season, you still found the soil salinity will be 4 deci per meter. So that situation we call the steady state. Okay, so in and out will be the same, and there's no change in the soil salinity level. So that's what we are going to, that's what we're going to assume. And if you assume that, so what's going to, so let's say for steady state, for steady state condition. So one is salinity concentration. Salinity concentration during a season, and the year is constant or zero. It's not changed. The salinity is constant. Let's say the constant. So that means change is zero. So that's a delta MSW will be zero. This is the first thing. And the second is the in situ precipitation, right? Liquid to liquid or solid to liquid is negligible. Okay, the in situ precipitation and dissolution of salts is negligible. Okay, so that means you get MS will be zero. So that means from the soil parent level. So you got some salts already present in the soil. So once you add water, so the salts are going to dissolve in the water, and that's kind of an addition. So that we are neglecting, that's MS. And the dissolution, that's MS, and the precipitation, that is MP. So MP is, suppose your concentration in adding up, and there is no space for, so obviously if the concentration is more, the precipitation is going to take place, right? So that also we are assuming it is zero. And then we also assume that there is no salts adding from the application of fertilizers and all. So that's a zero, right? This is second assumption. And then so let's assume that the crops are uptake salts will be zero. So that means CPW will be zero. The crops negligibly small. Okay, the crops are going to extract the salts which are negligibly small. So considering these three assumptions, and if you substitute these in the salt balance equation, so you will get that VICI plus VRCR plus VGCG, okay, minus VDDCDD plus VSDCSD, okay, is equal to zero. Because once you substitute all these things back into the conservation of mass equation, then you get a zero here. And now what are we going to do here? So now again we assume that the groundwater is not contributing. Generally groundwater is clean. Okay, either there is no groundwater interaction. So the mostly, since we are talking about the drainage, so there will be groundwater interaction, but the concentration of groundwater is zero. That's the CZ will be zero. So then VICI plus VRCR, okay, minus. So surface, both the concentration of surface and subsurface, the salts will be the same. Okay. And then if you collectively mention the drainage output, both surface and, you can combine these two and come up with like a V out. Let's say V out. This is all drainage out. Okay, drainage out and the corresponding drainage concentration out. Okay. Similarly, I will write this one V in and C in, which is, sorry, this will be equal to 0, and this is V out, C out. Or I can put in depth units instead of volume units, because mostly we're talking about the irrigation and all in depth units. So that the area term can be what you call hidden. So D in, that's the depth, input depth, minus C in is equal to, sorry, this is D out to C out. Okay. So this, you keep this. Now there is a term called, the leachate fraction, called a leachate generally denoted with LF. That's a leachate fraction. So what is leachate fraction? So leachate fraction is the fraction of the input water, so that to be applied in order to maintain the soil salinity levels, so that the crop production should not be affected with the soil salinity, the crop production. So that's leachate fraction is very important term. So that will tell you how much water to be added or applied to the field so that the salinity levels could be maintained. Okay, that's the leachate fraction. So here the leachate fraction LF will be equal to D out divided by D in, right? So this is leachate fraction, D out by Dn, which will be like a D seepage. We also call D seepage. So whatever the depth which is gone out from the root zone, so that one, and the depth to be depth of water to be added, let's say I. Okay, so if I put this in there in in LF in the first equation, so in this equation, sorry, so if I put this in this equation, so D in, so I can substitute, like I'm going to bring that equation down. I into C I will put the in, which is equal to deep out, so or you can go deep seepage into C out. Okay. So our interested is how much needs to be removed from the field and C out. So if I substitute this I into CIN, which is equal to, so if I substitute D seep, that is LF into I into C out. So what is the concentration you expect from the deep, from the drainage? That will be I into C in divided by LF into I. So I gets cancels out and C in by LF. Okay. So LF can be used to find out how much water to be applied, knowing the the drainage capacity, or let's say the coefficient of drainage. I'm going to talk about that, what is coefficient of drainage. And also that can be used to find out the concentration. Okay, so remember this. So the next part is, so from this the concentration can be replaced with EC, because we are talking about the salts. So the concentration here can be replaced with electrical conductivity. So that means EC the drainage water, let's say ECD, that's the drainage water, this will be equal to EC irrigation water divided by LF. Let's say this is a question number 1. And you can tag this, another equation we have, like LF is equal D Cpace by, earlier we talked about this, D Cpace or D out, or you can say, D Cpace divided by I, or output by input, let's say. So D Cpace also can be written like I minus DET divided by I. So here it is evapotranspiration. So that means if you have the field, suppose I is taking place, and this D Cpace is this, and this is ET. Okay, so I will be equal to ET plus D Cpace, or D Cpace is equal to I minus ET. So this is what we put the things together. Okay. Now, so now LF is equal to, so since LF is equal to EC from equation 1, LF is equal to EC IW divided by EC DW. So after having many experiments, the scientists proposed a generalized, equation for this is EC DW. So for EC DW, so what they observed, this is 5 times of ECE minus EC IW. Okay, this is after having, so this one will be this one. This is LF. So remember this equation, 5 times of ECE. ECE is the EC means electrical conductivity of soil, right? Of soil extract. Of saturated, it's called saturated soil extract. So I already mentioned what is saturated soil extract. You take a soil sample, right? You saturate it, and then you extract the water from, the saturated mass, and then find out the electrical conductivity of that particular, extracted water. So that will give you the soil salinity. Okay, that is ECE. So knowing that, and knowing the electrical conductivity of irrigation water, right, you can find out what is leachate or leaching fraction. What is leaching fraction? Okay, so 2 things here. Leaching fraction can be estimated with the concentration, right, terminologies, or you can also estimate it using these water terminals, water depths. There are the 2 equations. One is from the water depth leachate fraction. The other one is with the soil salinity leachate fraction, right? So remember the 2 formulas. So, all right. So there is an example. So we're going to talk about that example so that things will be clear on the Leachate fraction. Okay. Right. So the example here, so the irrigation water salinity, that is ECIW, which is equal to 1 decicement per meter. Okay. Applied water depth, that is the D in, is equal to 1176 mm per season. Crop water demand, that is ETC, which is equal to 1000 millimeter per season. Assume that plants extract 40%, 30%, 20%, and 10% of their water from the upper quarter, second quarter, third quarter, and lowest quarter of the root zone, respectively. First, determine the leachate salinity treating the root zone as a single layer. Next, determine the seepage salinity from each of 4 layers and the average salinity for the 4 layers. This is the problem. Okay, so that means you have another crop. Let's say this is the crop root zone. This is the crop root zone. So it has 4 zones, 4 soil zones. Generally what happened in the first, or which is immediately below the surface, so that's the 1 quarter. So the entire root zone is being divided into 4 quarters. Okay, so this is the second quarter, and this is the third quarter, and this is the fourth quarter, right? So this is all, you can see this is all the root zone. Sorry. So this is, yeah. So this is the root zone. So in the question, so generally the root zone is been divided into 4 quarters. First quarter, this, let's say this is the first quarter, second quarter, third quarter, fourth quarter. Okay, so from the first quarter, so generally what happened, there is a 40% of the ET, what you are showing here, evaporation. So the evapotranspiration contribution, you have to understand what is the contribution of ET from the soil root zone. So from first quarter, generally the 40%, second quarter 30%, third quarter 20%, and the last quarter that's a 10%. Right? You can see, I mean, it's obvious, like the layers which are close to in the soil surface, that will, result in a larger evapotranspiration compared to the layers which are, situated below the, the first quarter. So this is a kind of, the theoretical or the conceptualization, like a 40% from the first, 30% from second, 20% from third, 10% from the last quarter, right? If you consider the soil root zone as 1 layer, and again, you can divide that into 4 layers, okay, this one. So in the problem, So again, the problem, the irrigation water salinity. So obviously, so what is this? This is irrigation water is being applied, right? So that irrigation water, it has a salinity as well as, so I'm putting like a concentration, that's a CI, irrigation water, CIW, irrigation water, or let me put in the other way, like instead of CI, I'll put electrical conductivity, so that will be here. Yeah. So let's say ECIW, irrigation water, so that will be 1 decicement per meter. So that's irrigation water which has been applied. And I, irrigation water, is 1176 mm. This is per season. Okay. So 1176 mm per season. That's what happened. And ETC, that evapotranspiration, so that is which is going up, right? So that will be around 1000 mm per season. Okay. So the question here is, if this is the case, right? So ETC is this is also per season 1000 mm. So the 1000 mm is contributed like 40% from the first quarter, 30%, and 20%, 10%. So that's a distribution of this seasonal ETC, 10,000. Okay. So the question here is, so considering the whole root zone as one layer, find out what is the soil salinity and what is the individual soil salinity, right? When you apply like irrigation water at 1 decicement per meter. So that is the question here. So I mean, this as a root zone as a whole layer, one layer, you find out what is soil salinity, and like for each layer, like 4 quarters, right? Layer 1, layer 2, layer 3, layer 4. What is the individual soil salinity? So that's the question here. Okay. Now the solution. Okay. So the first, we have to find out the leachate fraction considering the single layer. So root zone as single layer. Okay. So if the root zone has single layer, so leachate fraction will be equal to, so I minus ET. So we have that equation divided by I, which will be 1176. This is the seasonal irrigation water, and the seasonal, ET is that, and then 1176. So you get the leachate fraction, which will be equal to 0.15. Okay, similarly, what is the electrical conductivity of this drainage water, which will be EC IW divided by leachate fraction. Okay, so which will be like 1 decicement per meter divided by leachate fraction is 0.15, and you get 6.7 decicement per meter. Okay, so what is the meaning of this? What is the meaning of this? So if you add the irrigation water with 1 decicement per meter soil salinity, okay, and then if there is a evapotranspiration of 1000 and the input of the irrigation water of 1176 mm, so the the soil salinity caused by the irrigation water in the soil would be 6.7 deci per meter. This is the thing. So this is considering the whole, root zone as a single layer. But what happens if you consider the individual layers, like first quarter, how much, second quarter, third quarter, fourth quarter? That we're going to see now. So for individual, what you have to do, I'm going to so if you understand 40% of ET the first quarter. If you see the picture again, so this is the crop and this is the root zone. Right, this is the root zone. So why the first quarter contributes more? Because the roots here in this zone will be larger. I mean, many roots. So similarly, the roots, number of roots will be less if you're going down. This is the ET. So in the question it is given, this contributes 40%. Right? 40%, that means the ET1, let's say ET1 will be 40% of ET. So that's the 0.4 times ET. Okay, this contributes. Then the second quarter, ET2 will be 30% of ET. And ET3 will be 20% of ET. ET4 will be 0.1 times of ET. Okay, so this, let's say, is a 1 quarter, second quarter, third quarter, fourth quarter. This is all. So now we have to find out the leachate fraction for individual layer, just like what we did in earlier. If you see exactly here, there are two quantities we are quantifying. One is LF and the other one is ECDW. This is for whole layer, but the same thing we do it for individual layers here. So let's talk about the layer 1, right? So for layer 1, this is for 4 different layers. So for layer 1, LF1 will be I1 minus ET1 divided by I1. So that is the equation. So now you find out what is I1 is initially. So this, for this layer, this is the I, right? So that's 1176 minus the corresponding ET will be this 40%. So that is 0.4 times ET 1000 divided by 1176. So the leachate fraction LF1 will be 0.66. Okay, so knowing the leachate fraction, now you find out what is the when the water is going down, what is the concentration of salts, that is EC1, the first layer. So that will be ECIW, irrigation water, divided by leachate fraction LF1, this one. So irrigation water, that is 1 deci per meter, and LF1 is 0.66. Okay, so then you get, so this one will be 1.5 deci per meter. So this is for layer 1. Let's say second layer. This is the first layer. Okay, for second layer, we have to do the same thing. LF2, find out what is LF2. So LF2 will be equal to, so what is the infiltration which is coming from the top layer? So that is LF2 is equal, let's say, I2 minus ET2 divided by I2. Okay, so this is the thing. So I2 is I1 minus ET1, right, by minus ET2 divided by I1 minus ET1, right? So if you see this for second layer, get this for second layer, so it's not I, so you have to take out this corresponding ET, okay? So that is what is the effective I which is going in? So that's we have to consider. Oh, sorry. Yeah. So that's why. So I1 minus ET1 will be the drainage which is going into the layer 2 minus the corresponding ET2 divided by 1 minus ET1. I hope this is understood well. So now I1 minus ET1 is already we have done in the before, in the layer 1, 776 minus ET2 will be 30%, right? Like 0.3 multiplied by 1000, right? Divided by 776, and this will be 0.61. This is LF2. Similarly, you have to find out EC2 because that's the concentration in the layer 2. EC2 is equal to EC1 divided by LF2. So that is 1.5. So earlier we have already measured estimated 1.5 dc per meter and 0.61. This is the leachate, and you get 2.5 dc per meter. So now third quarter, third layer, let's say, or third layer, similarly, LF3, which is equal to I3 minus ET3 divided by I3. So again, I3 means I2. So I3, that means I3 means I2 minus ET2 minus ET3 divided by I2 minus ET2. So that will be like 476 minus 0.2 into 1000, that's ET3 divided by 476, and you get 0.58. Okay. Now the corresponding EC3. So EC3, which is equal to EC2 divided by LF2, sorry, LF3. So which will be equal to 2.5 divided by 0.58 and 4.3 deci per meter EC3. So then the last layer, that's the fourth layer. Again, you have to find out what is LF and what is EC. So LF4 is equal to I4 minus ET4 divided by I4. Right. So this will be like 273 minus 0.1. So minus 0.1 into 1000 divided by 273. So this I4 is I3 minus ET3. So that's earlier we found out that. And so this will be 276. This is 276. All right. So this will be 0.64. You get, and then the corresponding you know, EC4, which is equal to EC3 divided by LF4. So EC3 is 4.3 deci per meter and 0.64. You get 6.7 deci per meter. If you observe these two quantities, you see this 6.7 deci per meter at the last layer, and if you see the entire root zone as a one layer, right? The entire root zone as one layer, how much you get? That is 0.15. We didn't do this. 1 divided by, I'm sorry, I think there is some mistake here. Yeah. So LF1 is 0.66 and 1 by so this is 0.15. This is 0.15. Okay, not 0.6. 0.15. So if you put 0.15 here, and so this will be 6.7 deci per meter. So the point here is, if you consider the whole, like all 4 layers in the single layer, you get 6.7 deci per meter, and that is also clearly seen here. The last layer, this is the last layer. If you see, that's 6.7 deci per meter. So it's a matching. Okay. So what is the average? What is the average? So that means, so you have one layer here, second layer, and third layer, fourth layer. Right, so these are the soil layers. So from here, so initially there is a 1 deci per meter is going in, and out will be, let's say, so out will be 6.7 deci per meter. So in is with the irrigation water. We are not considering, the soil saline originals are the salinity level which is already present in the soil. We are considering what is in, what is, what the soil salinity caused by irrigation water we are considering. Okay, so that is one, and 6.7 deci per meter. So let's look at this. Right, 6.7 deci meter. So if you add 1 deci per meter, and you get 6.7 deci per meter from the root zone. So then now in the second layer, so EC1 from one layer to second layer, this layer. So what we observe is this will be 1.5 deci per meter, and the second layer you get 2.5 deci per meter, and the third layer 4.3, and the sixth layer 6.7. Okay, so you can see how the salts are being accumulated from layer to layer, and finally at the last layer you get, quantity, the concentration will be high. So the average, or you can say the average soil salinity will be 1 plus 1.5 by 2 plus 1.5 plus 2.5 by 2 plus 2.5 plus 4.3 by 2. So layer to layer. Plus 4.3 plus 6.7 by 2. How many quantities? 1, 2, 3, 4. I am going to say 4. Okay. So now with this, you will get EC average, which will be equal to 3 decicement per meter. Once you do the math, you get 3 decicement per meter or average within the soil root zone. So this is the problem. And then so we have like half an hour left. And we also know the what is the irrigation depth, so that I mean this is with the evapotranspiration, but what is the irrigation depth really required in order to avoid the stress due to soil salinity? So that we are going to see the irrigation depth and leachate fraction has got some relationship. It's called leachate fraction and irrigation depth. So here we are directly talking about the soil moisture. Okay, and earlier we are talking about the evapotranspiration. So now, so how this? I mean, we need to add the two components here, right? So what the water effect could be on water effect on plants could be, one is evapotranspiration, soil moisture. Evapotranspiration, fine. We just defined now what happened if there is a soil moisture reduction, or in order to link this leachate fraction with the soil moisture. So how the equation would be. So I'm going to bring the same equation back here. So that is LF, the ET equation, that is LF, which is equal to I minus ET divided by I. So this is leachate fraction. We already know this equation. So we're going to modify the same equation and bring the soil moisture terms into picture. Okay, so this will be like 1 minus ET by I. Okay, or ET by I, which is equal to 1 minus LF. Okay, or I is equal to ET divided by 1 minus LF. Okay, so now I'm going to substitute this ET or replace the ET with soil, water, in terminology, water terminology. So to the terminology used for defining soil water. Okay, so that will be like I is equal to. So I'm going to do I. So ET is what? ET is when you have the enough soil water. So that means not reduction in soil water. So there is some soil water that is required for the crop growth that would not reduce, the crop yield. So we call that as readily available water. So we'll put readily available water, because this readily available water is not going to affect the crop growth, because once the readily available moisture content is achieved, and after that you will count on the manageable allowable deficit, the water deficit we call. So that means you can go for water deficit from the field capacity. So if you see this, uh, so if this is theta s and this is theta f, okay, theta s is full of water. So that's saturated condition. Theta f means so the water which is removed from the soil through gravity, right? So the water is held with, you know, forces like adhesive forces and capillary forces and all other forces. So that's the the field capacity. So that means soil can hold this water, right? Uh, because this is not influenced by the gravity. Gravity water is already gone, right? So whatever water which is here, this is already gone, and we call this is gravity water. But after theta f, so there's still moisture, right? So if you can grow the crops at theta f, right, you get yield, no yield reduction, you get YP, right, yield, potential yield. Then after that, you start reducing the soil moisture. Why do we reduce the soil moisture? Because I mean, water is the main concern. So you cannot keep every time theta f, okay? But still you can reduce the soil moisture. That may not affect the root, I mean, the crop yield, right? If that soil moisture is, existing, so that we call this is like a threshold. We call it threshold theta t. This is threshold moisture. So for which you still have YP. Okay, you still have YP. Then after that, if you go, so let's say here somewhere you will have theta wilting point, permanent wilting point, let's say PWP here. Here permanent wilting point. So if you cannot go up to this, so the plant is going to dead or die. This is the dead plants, let's say. So at this moisture content, plant is not, going to survive. So here you get this. Here we call Y0. So there is no yield at all. Okay. So this is a threshold. Remember, this is a threshold. The threshold is important, and the moisture content at threshold we call RAW. That's readily available moisture content. Always you compare with so this is available moisture content. Available moisture content. So that will be let's say AWC, available water content. That will be theta F minus theta permanent wilting point. This is the maximum. I mean, this is available moisture content, right? This is the maximum. Let's say maximum available moisture content. This is the maximum. So available moisture content or total available moisture content, that will be theta minus theta PWP. So theta is the current, right? The current moisture content that's available, currently available moisture content. Now, if the theta is theta T, so we called RAW. RAW is theta T minus theta WP, permanent wilting point. So this is a threshold. Threshold from threshold moisture content to this. So this is the moisture content. You cannot go beyond this moisture level. If it is you're going down, that means available moisture content will be shrinking, and that will affect your yield. Okay, so the point here is at theta t, still we are good, and that's not going to, affect the atmospheric demand. That's ETC. That's what you call pumping, right? So, I mean, plant can easily pump water to the atmosphere. That's not going to affect the ETC and not going to affect your yield, right? So that's why we're going to replace that with RAW in the earlier equation. That is I is equal to, I'm going to bring that equation back here. Okay, so I'm sorry. So, so the point here is I is equal to, okay, ET ETC by 1 minus LF or RAW by, I would put like irrigation efficiency, because it all depends on, if you estimate RAW and when you use the device to supply this irrigation, it all depends on what is the irrigation efficiency. Okay, if it's not, the devices are not 100%, or you may not be applying water 100%, what is, meeting the RAW. That's why you put the IE, irrigation efficiency, and then 1 by 1 minus LF. Okay, so the equation here is I is equal to readily available water divided by IE, irrigation efficiency, multiplied by 1 minus LF. And since it is, I mean, this is, since the irrigation efficiency will be percentage, so then you need to divide by 100, that will go, 100 will go up, and then you get in centimeters if, RAW in centimeters. Okay, so remember this equation. We're going to have an example here. This is an example. So some of the terminologies I think you're familiar from the irrigation module. One is like MAD, what is manageable or management allowable deficit, that is 45%, right? And then irrigation efficiency is given as 70%. Okay, so and then you got like TAW, like a total available water, which will be 24 centimeter. That's the total available water. Okay, and then ECI, irrigation water concentration, the salt concentration, 1.09 decicement per meter. Okay, and ECE, which is the soil, EC, that's 2.2 decicement per meter. Okay, so then in order to manage the salts, what would be the inflow? That's the I, irrigation depth you need to consider to maintain the salts. Okay, so that's the question here. So what is I? I will is equal to how much? I means small I here, I'm putting its capital I. Okay, by knowing MAD, so our equation is what? Our equation is I is equal to RAW divided by IE into 1 by 1 minus LF into 100. So this is the equation. So find out what is RAW. RAW will be 45% of TAW. Okay. So that is MAD multiplied by TAW, which will be 0.45 multiplied by 24. So which is equal to what is 0.45? So so let's keep it, or maybe you can find out. Should have the calculator now. That's okay, and the calculation will come. So this is the RAW value, this in centimeters. Okay, right. And then, so you have to find out what is LF. Okay, so LF is equal to ECIW divided by 5 times ECE minus ECIW. So this equation is already given. And now 1.09 divided by 5 times. So ECE is 2.2 minus 1.09, which is equal to 0.11. That's the Leachate fraction. So knowing the Leachate fraction and RAW and IE, so you can substitute in the equation and find out I, capital I. So capital I is equal to RAW by I, irrigation efficiency, into 1 by 1 minus LF into 100. So RAW, that's a 0.45 into 24 centimeter, that's the total available water. And so this is 70% irrigation efficiency multiplied 1 by 1 minus 0.11 into 100. So which will be like a 17 centimeter is the irrigation depth you need to apply. So this irrigation depth would help not only meeting the evapotranspiration or readily available water, and also it maintains the salts. Okay, so that is the meaning of this 17 centimeter. All right. So the next part is, so we are talking about salinity. So as I initially indicated, the salinity is the the aggregate term representing the the salt content. So it could be like a sodium salt, potassium salt, magnesium salt, calcium salt. So all these things. So it gives the total information. And dominant the cations would be calcium and magnesium in case of salinity. There is a sodicity. There is a term called sodicity. So in case of sodicity, the sodium content or sodium is going to dominate here, right? So Na plus is going to dominate, right? In case of soil salinity, also in case of saline soils or salinity, sodicity, right? There are two terms. Salinity, mostly the magnesium, calcium salts are going to predominate, whereas sodicity, the sodium is going to predominate. Okay. So in order to represent sodicity, we have a term called sodium adsorption ratio, that is SAR. Sodium adsorption ratio, we call SAR, okay, which is defined as, this is Na plus, concentration of Na plus and the square root of calcium concentration plus magnesium concentration divided by 2. So notice for, right? So basically there are three cations we need to consider for sodicity: sodium, calcium, magnesium. Okay. So the SAR is important. The value of SAR for the different soils will explain whether the sodium content is hazardous for the plants or not. Okay, so not only salinity, So you also should know the sodicity. Okay. So knowing these two, salinity and sodicity, like EC and SAR, right? EC value and SAR value. So these two values are important in order to understand the, you know, the degree of hazardness to the plant. Okay. So, for example, if ECI, so there is a table. I'm not going to. I'll give you the reference to the table. Maybe if you have some time, just go through the table. The table will really give you the hazardness. Let's say sodicity hazard to soils as a function of irrigation water. So in this is a table. So in this, the first column will be SAR. So now you find out SAR value, and then other values are like EC, irrigation water, electrical conductivity. So if you have the soil SAR and electrical conductivity of irrigation water, so whether this, the situation will hazardous to the plants or not. So suppose the SAR is from 0 to 3 and EC, so let's say the different hazardous levels, none, and then slight to moderate, okay, and then severe, right? So this is a degree of, we are talking about whether this particular condition is hazardous to the plants or not. So as SAR value 0 to 3, and if EC, 0.7, more than 0.7, irrigation water, electrical conductivity, then that's called none. So you're good to use that irrigation water, right? So with the soil, I mean this constituent, like calcium, magnesium, sodium of soil, find out SAR, and then find out what is the salinity of irrigation water. Okay, and now you have to see if that particular irrigation water is good for this particular soil, right? Suppose if your irrigation water is less than 0.7 decisimel per meter, and your SAR value is less than 3, then you're good. Your irrigation water is good. You can apply the irrigation water. Okay. Or if your irrigation water has the SARs, 0.7 to 0.2, okay, and this is slight to moderate. The severe is a 0.2, right? Soil salinity is less than 0.2, and SAR is 0 to 3. Similarly, there is a table. It will go like last point 12 to 40, and if the irrigation water is more than 5, and this is 5 to 2.9, and less than 2.9. So you need two values. One is SAR value and then ECIW value, and then you can understand whether this particular irrigation is, I mean, if you apply this particular irrigation, whether it's good for the plants or not. So that if it is not good, then you need to go for some kind of management. Okay. So that is the idea here. So let's do an example in SAR. So in this example, the sodium concentration, so that is given 460 milligram per liter, and calcium concentration, this is given 40 milligram per liter. Magnesium concentration, so this is given 24.3 milligram per liter. Then ECIW, which is 1280 milligram per liter. So this is the data is given. So the question here is, so in this situation, whether applying the irrigation water at 1280 milligram per liter electrical conductivity would be hazardous to the plants or not. So that is the question. So in order to understand, first find out what is SAR for this. So SAR will be Na plus divided by square root of Ca plus plus Mg plus plus divided by 2. So the units of this particular equation, this is milli equivalent per liter. Okay, the units here. So in this equation, so the units are milli equivalent per liter for all these things. So, but the equation, if you see this, we have the milligram per liter. So you need to convert that into milli equivalent per liter. Okay. So unit conversion. So the unit conversion here, milligram per liter to milli equivalent per liter. Okay. So in order to do what you have to do, so you have to divide the milligrams by the unit, the weight of the molecule or the atoms, right? And also the valence. Valence is important because here Na plus plus plus. Okay. So in order to convert that, so what I do? So for 460 milligram per liter, 460 milligram per liter Na plus. So this can be converted into 460 milligram per liter divided by 23, because one molecular weight of sodium is 23. Okay, and the valence is 1 plus 1. So divided by 1, still get 23. So this will be milligram per milli equivalent, MEQ. Okay, milli equivalent. So this will be 20 milli equivalent per liter Na plus. Okay. Yeah. So similarly for calcium, that is 40.1 milligram per liter Ca plus plus. Right. So this will be 40.1, right? Let's say 40.1 divided by 2. So this is a 2, valence is 2, and milligram per milli equivalent. Okay, so this will be like 2 milli equivalent per liter calcium. So similarly for magnesium, it's like 24.3 milligram per liter magnesium plus plus divided by, this is again 24.3 divided by 2, valence is 2 here, milligram per milli equivalent, and you get again 2 milliequivalent per liter magnesium. This for magnesium. So you converted all units into milliequivalent per liter. Now you can directly use the equation, that is SAR is equal to Na plus square root Ca plus Mj plus divided by 2, and Na plus that will be 20, and square root of 2 plus 2 by 2, and you get 14.14. Okay, and now we know SAR is 14.14, and ECIW ECIW is 2. It's like you see the ECIW, so that will be around 1280 ppm. 1280 ppm. So corresponding to that, the hazardous corresponding to that. So for SAR is equal to 14.14, and you get ECIW, that is 1280 ppm. Okay, so 1280 ppm. So then you get I mean, you have to go back to the table. So from the table, so 14.4, I'm looking at the table, that 12 to 20, and suppose the ECIW is greater than 2.9, you have 1280, so it is okay. So it's not going to harm, right? It's not going to harm. So no harmful, no hazardous. Okay, so you can apply to the field. Absolutely no problem. Okay, and the last is, what are the salinity management options? One is, if you see visually there is a deposition of salts on the surface, so you can remove surface soils. That's number one. I mean, this is a common sense, right? If there's surface, so you can just use scraper and then remove the deposited salts on the surface. Okay, scrapping or flushing. So you can use scrapes or flushing. Right? This is one. Okay, so then the other one is, if you have the salts present in the soil, you can remove by surface water by using drainage, and provide surface drainage system. So there are some engineering practices. So those are like, one is the leaching. And we talked about this, the leaching, what is leaching fraction and all. right? The second is the drainage. So the drainage could be like, surface drainage, subsurface drainage, and then natural drainage or non-conventional drainage. Okay, and we got also non-conventional, the mold drainage, vertical drainage. There's several things are there. And then third one is, artificial recharge. Artificial recharge. Okay, so artificial recharge in the sense, so you can, apply water on the top to vertical wells or recharge wells. So using through recharge wells. So that the salts can be leached to the groundwater. Okay. So then, these are the things. So we are going to talk about mostly the drainage part here as an engineering practice in order to control so not only the water which is staying on top due to excess input, but also removing the salts. So that is the advantage of drainage. So the drainage, what we talk in this course, we mostly focusing the field drainage. That means the drainage what we provide, so that should benefit not only to the soil but also to the farmer. That means production, in terms of production. So both soil health as well as the crop production. Okay, so these two things we need to keep in mind while designing the drainage, and also of course the cost. Right, so the drainage involves a lot of earthwork and laterals, and the field channels, preparing field channels, and all designing field channels. So it's a heavy cost involved in this. So before deciding for any drainage system, so you need to understand whether really the drainage system is required for this particular area or not. Okay. So suppose, generally the drainage will be provided if there is a problem constantly for the whole, the year, right? So suppose if it is for short term, for example, the field is inundated, or let's say the field is waterlogged for let's say 1 month, right? You don't need to provide drainage system for that. Okay. So if the water is stagnant for let's say entire year, then you have to think of installing or designing a drainage system, because that's a problem, and you are not going to use that the farm land for cultivation or anything else. So before going to abandon that, so better you provide a proper drainage system, so that will help, or that will keep the soil fertility as well as the you know uh, the farm returns, you can say the crop production or good yields. Okay, so the next class tomorrow we're going to talk about the agricultural drainage and their components, and why do we need this drainage system, and some terminologies. So what is the drainable porosity, and what is drainage coefficient, and also what are the major components of drainage system, typical drainage system. So all those things we're going to talk tomorrow. Okay. Have any questions? Let me know. Otherwise, we're going to uh, end this class. Okay. All right. So no questions. See you tomorrow.